Welcome to Study Loop.
Problem 710, we have a 25 kilogram child that plays on a swing, having support ropes that are 2.2 meters long. Her brother pulls her back until the ropes are 42 degrees from vertical, so pulled back and released from rest. So what is her potential energy just as she released compared to the potential energy at the bottom of the swing's motion? Okay, so part A, I'm just going to make it simple, and I'm going to start with having the potential energy be 0 when she's at the bottom. So when she's at the bottom, she's at the bottom of her arc. So I'm going to set that y1 equal to 0. And then I'm going to have when she was just released to be y2. And so basically, we need to find what the gravitational potential energy is going to be at this point. Okay, so we have some distances and we have some angles. So let's go ahead and try to figure out what we need. So we have the U gravity, and that's going to be equal to mg times some difference in height. Okay, so what's this difference in height? So that's just going to be y2 minus y1. y1 is 0, so we just need to find y2. We have 2.2 meters being this full height, but we need to find what this height is. So what I'm going to do is I'm going to use this length and this angle to figure out what this length is. And I'm going to take 2.2 minus that length, and that should give us this length here, right? Yeah. Okay, so we have a triangle here. We have a hypotenuse length, and we know that this is a right angle. So we can use the cosine of this angle times this length to find out what this length is. So that should just be 2.2 meters times cosine of 42. Okay, so then this distance should just be this total length, 2.2 meters, minus 2.2 meters cosine of 42 degrees. Okay, so then plugging that into our equation for the potential energy of gravity, we should have 25 kilograms times 9.81 meters per second squared times this distance. So we're going to have 2.2 meters minus 2.2 meters cosine of 42. Okay, and so just from here, that's math. So I'm going to write the answer, and that's going to be 69.3 joules. And joules unit of energy. So we have potential energy being 69.3 joules at the top of her swing of motion, or the difference when you find the bottom to be 0. Okay, so that's part A. Part B, how fast will she be moving at the bottom? So for part B, we need to find out some relationship between her energy here and energy here, and that's just going to be conservation of energy. So we're going to write K1 plus U1 is equal to K2 plus U2. Okay, so we've already decided that we're going to have potential energy be 0 here at the base, so that's gone. We know she starts from rest, so that's gone. So we just have the potential energy at the beginning, which we already know, equal to the kinetic energy at the base. So we can just solve for that velocity there at the bottom. So we have 69.3 joules equal to 1/2 mv squared. Okay, so here, that's just math from here. So we can do 2 times 60 times 69.3 joules. That's going to be divided by 25 kilograms. I'm going to take the square root, and that's going to be equal to v, and in the end, that's going to be equal to 2.4 meters per second. That's our solution for B. Okay, and then C, how much work does the tension ropes do as she swings from initial position to the bottom of the motion? Okay, so I'm going to go to a new page, and we're going to have the point where the line starts, where the rope starts, and it's going to be where that girl is. And I'm going to write two vectors that will show what is happening here. So we have T for tension, right? That's what the rope does. It pulls her towards the point there. The rope can only pull. And we have the displacement as she's traveling. So that's going to be our, should write a vector there. So that's going to be our displacement vector there. So I'm just going to write S for that displacement. And I'm going to do that again for one more point. We have here, we have again the same vector. It goes straight along that rope, but her displacement vector changes a little bit because it's going more in that arc. Sorry, it's not a perfect arc there, but that's going to be the direction that she travels as she goes down that arc. And what we see is if you extrapolate this to every point in her path of travel, that she's going to have her tension be perpendicular to her displacement vector. So that means that when you calculate the work done by tension, that is equal to the integral of the force dot product with the path of travel. What you're going to have is you're going to have at every point, you're going to have them be perpendicular. So that means that dot product goes to 0. So that shows us why the work done by tension is 0. Okay, so that's the solution to this problem.